Welcome along to the next video in this series called Exploring the Solar System. My name is Dr. Alan Wood and I'm a senior lecturer in the physics team at Nottingham Trent University. So this session is called The Dance of the Worlds. Now, in the last session, we were talking about the model of the universe proposed by Copernicus that put the sun not just at the center of the solar system, but the center of the entire universe. Up until that point, Ptolemy's model that put the Earth at the center of the universe held sway. Why did Copernicus propose a heliocentric model? Well, Ptolemy's model was really complicated, and it could be modified in several different ways to match the same observations. So Copernicus thought, well, if it could be modified in this way or that way to match the observations, well, one way is clearly wrong, so why not both? However, there were problems with Copernicus's model, and it took a long time for it to hold sway. We talked about some of those last time, and the most important of these is it didn't work as well as Ptolemy's model at explaining the observations. And it didn't work as well until the work of Kepler and Tycho Brahe was undertaken. And that's what we're going to look at this time. So let's first of all think about Johannes Kepler. Well, Kepler was originally interested in the question of why are there 6 planets? And Copernicus's model of the universe proposed that the planetary orbits were circular. And Kepler was thinking, well, there's 5 regular solids nested within one another, and if we nest them within one another like this, well, then that gives 6 circular orbits. So maybe that's why there's 6 planets, because it's something to do with the geometry of this problem here. And this was a theory that he absolutely treasured. But the observations and the theory disagreed. He tried to use this theory to say, well, we now can work out the distance to these planets, therefore, let's see if we can predict their positions. And it just didn't work. Not by much, but it didn't work. And so initially he thought, well, maybe his observations weren't quite good enough. So he journeyed to work with Tycho Brahe. And work with is a bit of a strong term here. Kepler and Tycho did not get on at all. Kepler was a very quiet, studious individual. Tycho, he liked to party. It's said that he had a golden nose because him and another mathematician, when they were students, had a duel about who was the better mathematician. And he lost a bit of his nose in that process, and it was replaced with a golden nose. And he certainly liked to party. He would throw these massive banquets, and at these banquets, he would then announce some of his astronomical observations. And Kepler had to go along to these to try and get some of these observations, and he absolutely hated them. But the two of them respected one another, and when Tycho passed away, he bequeathed his observations to Kepler, and Kepler used these observations. He compared, and he saw that his theory simply didn't match observations. So in the very best scientific tradition, he rejected his theory and looked for a new one. So observations and theory did not agree. Plus, of course, Kepler's theory couldn't explain the motion of moons. Why it could possibly explain planets in terms of its original form, but it certainly couldn't explain things like the moons of Jupiter. So Kepler came up with 3 laws of planetary motion. These were based on the observations of Tycho Brahe. So these are what's called empirical laws. They tell us what happens, but they don't tell us why. And the first of those is a planet moves in an elliptical orbit with the sun at one foci. So Copernicus thought that the planets went in circular orbits. Kepler showed they were ellipses. And suddenly that made Copernicus's heliocentric model of the universe work. Suddenly, observations and theory began to match. Kepler also observed that a line from the sun to a planet sweeps out equal areas in equal times. So it takes a certain amount of time for the planet to go from this point here to this point here. It takes a certain amount of time for the planet to go from this point here to this point here. Now, those times are the same to make the areas the same. So it means as the planets get closer to the sun, they move faster. And this also made Copernicus's model of the universe work. There's all sorts of parameters that we need to think about when dealing with elliptical orbits. But the one I'm going to focus on here is just the semi-major axis. So here's our ellipse. The sun will be at one foci, either here or here. And the semi-major axis is this parameter here, the distance from the center of the ellipse to the edge. And because planetary orbits are not very elliptical, we tend to think of this as the distance between the sun and the edge, because the sun in this scheme is really here or here. It's close to the center. Now, we're now going to think about Kepler's third law. Kepler's third law relates the orbit of a planet to the semi-major axis. And if we just take planetary periods throughout the solar system, and we plot those, and we plot the semi-major axis, which is sort of like the mean distance from the sun to the planet, we see it looks like there's a bit of a pattern there. And Kepler was able to turn this into a law. And in his law, this would become a straight line graph. So what I'd like you to do is, here are the data that Kepler had available to him, the orbital periods and the semi-major axis. And I would like you to use these data to try and find a mathematical link between the orbital period and the semi-major axis. So what will our mathematical link look like? Well, it means if we have a graph, rather than it looking like this, it will be a straight line. So try to plot these data and then try and plot various versions of it. Maybe you might look at the square root of the semi-major axis, or you might look at, say, the cube of the orbital period, and try these things in different combinations and see if you can get to the point of finding a straight line graph. So that's what I'd like you to have a little go at, please, and we'll look at the solution to that in the next video. If you can come up with a straight line graph, then you have just found Kepler's third law for yourself. So thank you very much for your attention, and I will see you in the next session.